Good evening, ma'am. Am I audible to you?
Good evening, sir. Yes, you are audible, sir.
Okay, ma'am. Thank you so much.
Good evening, sir.
Yes, good evening. Have you completed the test which I sent you yesterday?
Yes, sir.
Okay, very good.
Sir, you can start now, sir.
Okay, ma'am. Okay. Good evening, students. So, yesterday I gave you a question paper containing 15 questions, 5 questions, sorry. So, I think you all might have completed the test. So, today I will be discussing the solutions for those 5 questions which I had sent to you yesterday. So, let us first start with the question paper discussion now. So let me open the PDF file containing the questions and the solutions as well, so that we can quickly go through the solutions. Okay.
Sir, your screen is not visible, sir.
Is it visible now, ma'am?
Yeah, sir. Now we can see, sir.
Okay. Okay. So students, you see, this is the first question. Okay. First question which I had sent you yesterday. The radius of the circular conducting loop shown in figure is R. Magnetic field is decreasing at a constant rate alpha. Resistance per unit length of the loop is rho. Then current in wire AB is. AB is one of the diameters. This is the question. You can see the radius of the circular wire, circular loop has been given as R. Magnetic field is decreasing at a constant rate alpha. They are asking us to calculate the current in the wire AB. Okay. So for calculating the current, we actually have to apply the Ohm's law, I equal to E by R. Okay. That is the induced EMF divided by resistance. So that formula we need to use. If we have to use the formula, we need to find out the EMF induced in the wire AB. Okay. So that part first we have to do. The EMF induced across AB. First of all, we need to find out that. So EMF across AB. So that is d phi by dt. As you can see from the PDF file. Okay. So you see here, EMF across AB equal to d phi by dt. D by dt of, instead of phi, you need to substitute B into A. Magnetic induction into area. Here area is constant, so I am taking it out. So area is taken out, and you will be having dB by dt. So this dB by dt is the rate of change of magnetic flux. In the question, it has been given as alpha. Okay, and the area you should see here carefully. So here we are discussing about the EMF across this AB. Okay, across this AB means at one time you need to consider the semicircle. Okay, across AB means you have to consider the semicircle. Semicircle means when you take the area, you should take only half of the area of the circle. So that's why I have taken this thing pi r squared by 2. Okay. Now in the upper semicircular loop, the resistance across this AB we need to find out. So the resistance is actually calculated using the formula resistance per unit length into half of the circumference, because we are considering only the upper semicircular loop. So upper semicircular loop means it is actually half of the circle. So that is the semicircle. So resistance per unit length rho multiplied by the length of the loop. Length of the loop means it is actually half of the circumference. So that is pi r. Okay, 2 pi r is the total circumference of the loop, and when you divide it by 2, you will be getting pi r, and it is rho pi r. It is nothing but the resistance across AB. Okay, for the upper semicircular loop we are discussing now, that is rho pi r. And as I have told you, we need to find out the current. It is EMF by resistance. So current in AB due to the upper semicircular portion, that is EMF by resistance. EMF we have already calculated here, pi r squared alpha by 2. So that thing I am putting here, and resistance is rho into pi r. Why it is rho into pi r? Rho is resistance per unit length multiplied by half of the circumference of the circle, that is pi r. So in denominator you are having rho pi r. So when you simplify this term, pi r squared alpha by 2 divided by rho pi r, you will be getting r alpha by 2 rho. Okay. So this is the current in the portion of the wire AB due to the upper semicircular portion of the circle. Okay, upper portion of the circle. So this current is usually in clockwise direction. Okay. So let me show it here. So here you can see it is in the clockwise direction, like this. So the current in the upper portion, usually it is like this. Okay. So similarly, you can calculate the current flowing through AB due to the lower portion of the circle, that is lower semicircular portion. So when you use the same formula, okay, so that also I will discuss now. You will be having the same formula for the lower semicircular loop also. The resistance is rho pi r, and the current is given by EMF by resistance. So that EMF is nothing but pi r squared alpha by 2 divided by rho pi r. So when you simplify all these things, you will be getting r alpha by 2 rho. That is in the anti-clockwise direction. So currents in both the upper and lower portion, they are in equal in magnitude but opposite in direction. So they will be cancelled out. So what happens is the net current through AB will be 0. That is option D. Okay. Do you understand the solution for this problem? Anyone have any difficulty in understanding this?
No, sir.
Yes, students. Anyone else? If you have any doubt, please don't hesitate. Okay, you can unmute yourself and you can ask your doubts. So first question we have completed. The second question you can see, a magnet NS is suspended from a spring, and while it oscillates, the magnet moves in and out of the coil C. The coil is connected to a galvanometer. Then as the magnet oscillates, here you can see this arrangement. the magnet is connected to a spring like this, and you have a coil connected with the galvanometer. So due to the attachment of the spring, the bar magnet can oscillate to and fro. Okay, to and fro. That is, the magnet can come closer to the coil and it can also move away. Okay, due to the attachment of the spring. Now they are asking is, when the bar magnet oscillates, what will happen? They have given you 4 options, and what is the right options? Right option we need to choose. Okay, as you see here, the bar magnet is
Sir?
connected. Yes, yes, ma'am.
Sir,
Yes,
doubt, sir.
yes, yes. You please tell me.
Sir, for this question, sir, the answer will be, sir, could you scroll down, sir?
Yes, will do.
Sir, it'll be option D, right, sir? It shows deflection, but the amplitude decreases, sir,
Yes,
steadily.
G shows deflection to the left and right, but the amplitude steadily decreases. This is the answer for this question. Yes, any doubt? Yes, student, can you hear me?
Yes, sir.
Okay. So here you see the bar magnet actually oscillates to and fro. Okay. So it comes towards the coil and it can move away. So in this process, it executes simple harmonic motion. Okay, simple harmonic motion. So when the magnet comes towards the coil, there's a deflection in galvanometer, and when the magnet moves away, the deflection in the galvanometer is in opposite direction. But here you have a spring here and bar magnet here, and due to the presence of eddy currents, okay, eddy currents, there will be a decrease in amplitude of the oscillation. Okay, so due to the decrease in amplitude of the oscillation, the galvanometer deflection also slowly it stops. Okay, it stops means the galvanometer deflection amplitude also steadily decreases. Okay, because here the bar magnet oscillates to and fro while the amplitude of the oscillation decreases, and due to that the galvanometer deflection also decreases. Okay, with time. This is the answer for this question, and the right answer is option D. Okay, do you understand this, students? Any doubt? I hope there is no doubt to you. The next question you can see, the diagram below shows 2 coils A and B placed parallel to each other at a very small distance. Coil A is connected to an AC supply. G is a very sensitive galvanometer. When the key is closed, what happens? You can see this is the circuit, and here when the key is closed, what happens? You have a AC supply here. Okay, so the AC signals will flow through the circuit. AC signals will flow through the coil A, and due to that you will be having a time varying current flowing through the coil A. Since this coil B is very close to this coil A, what will happen? In coil B also there will be an induced current. Okay, because here the current flowing through the coil A, it is varying with time. So due to that, you will be having a time varying magnetic field, which is also linked with the coil B. So the magnetic field linked with the coil B changes, and due to that, you will be having induced current, and due to the induced current, the galvanometer will show deflection. Okay, but here what they are asking is, they are having 4 options here. Okay, among the 4 options, you should choose the right option. Okay. So here you see the correct option is option C. Okay, why it is option C means, you can see that oscillations in the galvanometer will be observed when the input AC voltage has a frequency of 1 to 2 Hz. In the other options, what you can see is constant deflection will be observed in the galvanometer for 50 Hz supply, or visible small variations will be observed in the galvanometer for 50 Hz input. These options can't be correct. Why I am telling like this? Because in the question they have mentioned that the G is a very sensitive galvanometer, So it is a sensitive galvanometer means even for a slight change of current flowing through the coil A, you will be having a change in magnetic flux with the coil B, and even that minute change in magnetic flux will lead to an induced current flow. The induced current flow, even if it is very, very less, the galvanometer will show deflection because it is a very sensitive galvanometer. So the frequency of AC signal here, if it is very high, what will happen? Since it is a very sensitive galvanometer, the induced current flowing through the coil B will also vary very, very quickly, and due to that, the galvanometer deflection will be very vigorous. So due to the very fast movement of the galvanometer deflection, when the AC signal frequency is high, okay, we can't actually observe that the galvanometer needle is whether moving or not, okay, because when the input frequency is very high, the galvanometer deflection also will be very, very high. Why it is very high? Input frequency high means the current flowing through the coil varies very quickly. Due to that, the magnetic field variation in the coil A is also quick, and due to the magnetic field variation in A, induced current flows in coil B, okay, and that induced current also varies very quickly, so the galvanometer deflection may be very, very quick. So since it's a sensitive galvanometer, for very high frequencies, the galvanometer deflection is very vigorous, and you can't actually distinguish whether the needle is at rest or it is in vigorous motion. So for very small frequency in the AC input signal, that is 1 to 2 hertz, okay, oscillations in the galvanometer will be observed when the input AC voltage has a frequency of 1 to 2 hertz. This is the right option, that is option C. Okay, I think you can understand this. If you have any doubt for any of the question, you can unmute yourself and you can ask your doubt. Then question number 4, an infinitely long cylinder is kept parallel to a non-uniform but constant magnetic field. Okay, actually it is non-uniform but constant magnetic field that be directed along positive z-axis. The direction of the induced current as seen from the z-axis will be. So you have 4 options and we need to choose the right option. Okay, infinitely long cylinder is kept parallel to a non-uniform but constant magnetic field. So this is the diagram. Infinitely long cylinder kept parallel, okay, to a non-uniform but constant magnetic field. So constant magnetic field means dB by dt equal to 0. Okay. So here the cylinder is kept like this, parallel to the uniform magnetic field. So along the z-axis, if you see what is the direction of induced current, they are asking. So for that we need to consider this Maxwell's equation, minus delta E equal to dB by dt. Okay. So that means whenever there is a change in magnetic field only, there will be an electric field. Okay, there will be an electric field in the cylindrical rod. Here, you know very well, this is a constant magnetic field. Okay, non-uniform but constant magnetic field. Constant means this dB by dt is equal to 0. So due to that, you won't be having any electric field. So when there is no electric field, the electrons in the conductor won't move. Okay, because usually the electrons in the conductor will be in random motion. So the net velocity is 0. Only when you have an electric field applied for this cylindrical conductor, the electrons in the conductor will start moving and you will be getting current. So if you want to have the electric field, this dB by dt should be non-zero. But in the question they have given non-uniform but constant magnetic field. So that means dB by dt equal to 0. So electric field is also 0. That means you won't be having any current. So the correct option is option C. Okay, it is 0. Then question number 5. An electron moves along the line AB, which lies in the same plane as a circular loop of conducting wires as shown in the diagram. What will be the direction of induced current, if any, in the loop? Okay. So you see, this is a circular loop of conducting wire and an electron moves along this line AB. Okay, electron moves along this line AB. So what will happen? Electron movement means current changing. Okay, electron is moving means current is changing or current is flowing. So when it is moving from left to right, the flux linked with the circular loop will first increase and then decrease as the electron passes by. Okay, so when the electron comes closer to towards the circular coil, there will be an increase in current. Due to that, there is an increase in magnetic field in the plane circular loop. But as the electron crosses this point and it moves away from the circular coil, there is a decrease in current, and due to that, there is a decrease in magnetic field also linked with the circular loop. Okay, so the magnetic flux initially increases when the electron passes from this point A towards the circular coil, and after that, what happens is the electron moves away. That means the magnetic field linked with the coil also decreases. So what happens is the current will change direction as the electron passes by. This is the right option. That is option D. Okay, the current will change direction as the electron passes by. Option D is the right answer. I think you all can understand the solutions for this problem. Okay, so now we shall move on to our discussion on electromagnetic induction. We need to discuss few more concepts in electromagnetic induction. So let us see. Yesterday we started with the self-induction. Okay. So today we are going to see the formula for self-inductance of solenoid. Okay. Self-inductance of solenoid. What is the formula for the self-inductance of a solenoid? So that is given by L. Okay. So L equal to mu naught N squared A divided by L. So here what is N? N is the number of turns in the solenoid. So N is the number of turns. And A is the area of cross section of the solenoid. And L is the length of the solenoid. Okay. And L is the length of solenoid. So this is the formula for finding out the self-inductance of the solenoid. Okay. So then we can have if you have the solenoid core, okay, solenoid core filled with any magnetic material of permeability mu. In that case, this equation is modified. Okay, L equal to mu N squared A divided by L. When the solenoid core is filled with, when solenoid core is filled with magnetic material of permeability mu. Okay. So when it is filled with magnetic material of permeability mu, then you will be having this formula. Okay, L equal to mu n squared A by L. And you can also have one more constant here, that is number of turns per unit length. You can also have n equal to number of turns per unit length. So small n equal to number of turns per unit length. When you have like this, then that is small n is equal to capital N divided by L. In that case, n equal to small n into L. So now what is the value of your inductance? That is mu naught n squared L squared A divided by L. So that will be mu naught n squared L into A. Okay, mu naught n squared L into A. This is the inductance. When you have the number of turns per unit length, that will be mu naught n squared L into A. And this L into A is nothing but the volume. Okay, volume of solenoid, L into A or AL. So in that case, L equal to mu naught n squared into V. So this is the self-inductance of solenoid, and I hope that you all know about the solenoid, okay, because we already have discussed what is a solenoid coil. So a solenoid coil actually looks like this, okay. This is how a solenoid coil looks like. We can supply current, then it will behave like a bar magnet, okay. This is the solenoid coil. We have already discussed this during our earlier discussion on magnetic effects of current. And we shall move on to self-inductance of toroid. Toroid is nothing but the circular coil. Okay. So self-inductance of toroid. So what is the formula? L equal to mu naught n squared A, okay, mu naught n squared A into 2 pi r, where r is the radius of the toroid and A is pi r square, okay. A is nothing but pi r square, that is area of the toroid or area of cross section of the toroid, and r is nothing but the radius of the toroid. This is the expression for self-inductance of toroid. Do you all understand this, students? Self-inductance concept. Do you all understand? Students?
Yes, sir.
Okay. Now we shall discuss something about inductor. Okay. So inductors we are going to. The symbol for inductor is like this. Okay. So inductance value, we all know very well, represented by capital letter L. So the self-inductance, okay, produced in the inductor coil, for different case we shall discuss now. So first case is you have a inductance coil like this, and the current, okay, current through the inductor is now increasing. So you have point A and point B here. So in first case, current through the inductor is increasing. Current I increasing. Then what is your equation? Your equation will be voltage at point B, at point A, minus L into di by dt. This is equal to V. Okay. So when current through the inductor increases, you will be having this equation. So the second equation is let me write it here. Current I so here you are having point A and point B. If the current decreases, okay, current I decreases, then what happens is VA plus L into di by dt equal to VB. Okay. So these are the scenarios for inductor. And an inductor usually stores energy. Okay, inductor usually stores electrical energy, and now we are going to see the expressions. Okay. So whatever energy is supplied by battery, it is stored in inductor. So what is the total energy stored in inductor? Inductor actually stores energy in the form of magnetic field. Okay. So energy stored in inductor. So if you have a circuit like this, and you have a resistance and inductor coil L, and you have a battery. So the battery is supplying EMF E. So current is flowing in this direction, that is anti-clockwise. Okay. So the inductor stores energy in the form of magnetic field. And what is the expression for the energy? So that we can write here. Energy stored in form of magnetic field in the inductor is U equal to half Li square. Okay, half Li square. The current can be taken as capital I here. So U equal to half Li square. Okay, U equal to half Li square. And you can have a solenoid here. It is nothing but a solenoid. Okay. So inductor coil is nothing but a solenoid. We all know very well the inductance. So just now we have seen the inductance value L is equal to mu naught N square A into L. This is the inductance value. So here, you know very well the magnetic field inside a solenoid is given by this equation. B equal to mu naught Ni. The magnetic field inside a solenoid B equal to mu naught N into I. So using this, you can write the expression for inductance. So L is equal to B square AL divided by mu naught into I square. Mu naught into I square. If you substitute the value of this induction here and you substitute I squared here, okay, you will be getting the expression for inductance written here. Okay, so B squared AL by mu naught I squared is the expression for inductance based on this magnetic field. Now using this value of L, you can find out the energy stored in magnetic field. What is that? So here U equal to half Li square. So when you substitute all the values, B squared by 2 mu naught into A into L. This is another formula for energy stored in an inductor. Okay, this is one more formula. And the energy stored per unit volume also you can take. So that is represented as small letter U. So small letter U is nothing but energy per unit volume. Okay, energy per unit volume. So that U is nothing but capital U by AL. Okay, so that will be B squared by 2 mu naught. Okay, B squared by 2 mu naught. This is energy stored per unit volume. Okay, so this expression energy stored per unit volume is derived for solenoid, but it is applicable for any cases. Okay, whenever you need to find out the energy stored per unit volume in an inductor, you can use B squared by 2 mu naught. Okay. Okay. Now we shall move on to the discussion of mutual inductance, mutual induction concept. What is mutual induction, students? Can anyone tell me? What is mutual induction? Students, can anyone tell me what is meant by mutual inductance? Yes, students? Anyone? You can give it a try. Okay, no issues. Even if you are wrong, it's not a problem. You can unmute yourself and talk. What is meant by mutual induction? Anyone can talk, no issues. You can unmute yourself and talk. Okay, just now we have discussed in a numerical problem, I think. Okay, let me show that again for you. Here you see. Okay, here you see. This is a coil. This is called primary coil because through this coil only you are having current flowing. Okay, so current is flowing through this coil A through an AC source. So due to the flowing of current, and another coil adjacent to the primary coil. So this can be taken as primary coil. So this is nothing but secondary coil because with the secondary coil you have no current source connected directly. You have only a galvanometer connected here. Due to the movement of current through this primary coil, you are having EMF generated in the secondary coil and also induced current. Okay, due to the movement of current in one coil, EMF and current are induced in secondary coil. This is the concept of mutual induction. Mutual induction means flowing of current in one coil causes induced current in second coil. Okay, this is called mutual induction. Okay, this is called mutual induction. So now we will be discussing the mutual induction concept. So if you have two coils of inductance L1 and L2, okay, L1 and L2, what is the value of mutual induction? So mutual inductance is represented as capital letter M, that is K into root of L1 into L2. For two different coils having self-inductance L1 and L2, the mutual inductance M is given by K into root of L1, L2. Here K is called coefficient of coupling. Okay, K is called coefficient of coupling. And for tight or close coupling, okay, you have some cases here. For tight or close coupling means that the two coils are kept very closer to each other. So in that case, K equal to 1 actually. Okay, K equal to 1 actually. And in that case, this M is nothing but root of L2 into L1 into L2. Okay, L1 into L2. And for loose coupling, you will be having the K value lying between 0 and 1. So these are the different cases. Okay, these are the different cases. So you can be having various ways in which you can couple the two coils. The coils can be kept like this. Let me draw it here, okay, for your better understanding. You can have the primary coil like this and the secondary coil like this. This is one way of coupling. Okay, this is one way of coupling. That is normal coupling. That means planes are parallel. And you also can have another way of coupling. That is one coil is like this and another coil can be kept like this. Okay, at 90 degree. So this is called parallel coupling. So this is called parallel coupling. This is 90 degree fashion. Okay. If the same arrangement, okay, if the same arrangement of these coils, if the secondary coil is kept far away from the primary coil, then there will be no overlapping or zero coupling. Okay, So that also can happen. So these are the different ways in which you can couple the two coils. Okay. Now we can discuss the concept of mutual inductance of two solenoids. Mutual inductance of two solenoids we can discuss. Okay, mutual inductance of two solenoids we can discuss. So you can have one solenoid like this. And one more solenoid coil is oriented like this. So this is one solenoid. S2. And here you are having the second solenoid. Second solenoid like this. So this is S1. Okay, this is S1. So you can calculate the mutual inductance between these two solenoids. So that can be written as M equal to mu naught N1 N2 pi R1 squared whole divided by L1. This is the mutual inductance formula. N1 and N2 are the number of turns in solenoid 1 and 2 respectively, and R1 is the radius of solenoid 1. Okay. So this is the mutual inductance formula, and you can have different cases also, of course, here. So the two mutual inductance can be in the form of concentric and coplanar coils also. Okay, so that also we can consider now. So here you have one coil. Here you have another coil. So this is radius R1. And this is radius R2. So this is R2, and this outer solenoid is having the radius R1. So here R1 can be greater than R2. So the mutual inductance can be represented like this, equal to mu naught N1 N2 pi R2 squared whole divided by 2 R1. Okay, two concentric and coplanar coils. For that, mutual inductance can be represented like this: mu naught N1 N2 pi R2 squared divided by 2 R1. Okay, so two concentric and coplanar loops, you can have it like this. And from this, what you can understand is this mutual inductance is directly proportional. Okay, it is directly proportional to R2 squared divided by R1. And you can have another scenario. Okay, this is first case. And second case also you can have. The second case you can have concentric and coplanar circular loops. Okay, concentric and coplanar circular loops. So here you can have one coil like this and another coil can be like this. Okay. Sorry, it is square loop. It is not circular loop, it is square loop. Square loop. So the side of this square, outer one is, can be considered as A, small letter A. And for this smaller thing, smaller square, actually it may look like a rectangle, but it is a square, okay, but it is a square. We should not think that it is rectangle, it is nothing but a square. So this side is nothing but B, okay, B. So here the mutual inductance is directly proportional to B squared by A squared. This is the next case. And you have a third case. In third case, you have a square and a circular concentric. And the coplanar loop. And the coplanar loop. So here you may have a square like this. And inside the square you may have circular. Loop like this. The radius of this circular loop is, where is the circular loop? Okay. Here you see this is the circular loop. And the radius of the circular loop, small letter E, okay. And the side of this square is, this is small letter R and this is A. So you see, side of this square is A. So here the mutual induction is directly proportional to R squared by A. These are the different cases of mutual inductance of solenoids. Okay, these are the different cases. You may get numerical problems based on these cases. Okay. So once again, I will be back. So then we shall move on to the next concept. So the next concept is series and the parallel combination of inductance. Okay, series and parallel combination of inductance. That means if you can have two inductor coil like this, okay, connected like this. This is a series combination. So here, what is the total inductance? Okay, what is the total inductance? So the total inductance is given by. So the inductance of this coil is L1 and this coil is L2. The total inductance is given by Ls equal to L1 plus L2 plus or minus 2m. So when the solenoid coils, when there is no coupling, okay, when there is no coupling, then for this case, your m equal to 0. So that means L1 plus L2 will be your Ls. For the second case, when the two coils support each other, when the two coils support each other, then you will be having Ls equal to L1 plus L2 plus 2a. When the two coils oppose each other, then you will be having Ls equal to L1 plus L2 minus 2m. Okay. This is the expression in case of series combination. And of course, now we will be discussing the parallel combination. So the parallel combination of inductors. So here we may be having the inductor coil connected like this. Okay. Connected in common. You may be having current applied like this. So this is L1, this is L2. Then the total inductance is 1 by Lp equal to 1 by L1 plus 1 by L2. So that means Lp equal to L1 L2 divided by L1 plus L2. So this is the parallel combination of inductance. Okay. So we shall stop with this. Okay, in this class, and we shall continue our discussion on electromagnetic induction in our next class. Okay. Tomorrow you will be getting another question paper having 5 questions. Okay, please attend the test, and we will be discussing the solutions of that test on Thursday. Okay, that is our next class. Thank you so much for joining the session.
Thank you, sir.
Thank you.